All right, so there are 4 techniques to finding delta H, and when you get these questions on the AP exam, it will just say, all of them will say, find delta H using the following data table below or information below. And you have to just go through the data table and figure out what information is being supplied for you. So one of the data tables you already did is the one that is bond enthalpies, where it gives you something like that, right? Or C-H. So you would do bonds broken minus bonds formed, right? You draw the structure, you figure out how many bonds there are, and then bonds broken minus bonds formed. You know how to do calorimetry because you're a master at it now. And then today we're going to learn how to do Hess's law and enthalpies of formation. This one's not hard, but I would say it's the second hardest out of this. And this is a simple equation that you're going to use very similar to this. This is probably the easiest one. So tonight's homework, there are values here that have to be looked up. And I don't give you guys a textbook, so that's where you would find them. So I posted on Google Classroom a link to a website that provides all of those values for them. And if you need me to print it up for you before you leave, I will. Wrong one. Okay. Hess's law. Basically, this is an example of making pit stops on a road trip. If I'm trying to go from New Jersey to LA and I'm driving, I have to make some stops along the way, right? So maybe I drive like 200 miles, and maybe I drive like, I don't know, 500 miles. And I keep going along the way. Eventually, I'm going to travel the full distance, right? Like somewhere around 2,000 miles, I'll get there. But the sum of all of those pit stops are the same distance as the entire trip, right? If I'm calculating delta H, I could figure out the overall delta H for a reaction by doing it in one step or doing it in multiple steps. And then I would just sum them all up. That's essentially what this says. It's always going to be, though, for the final step the same. Maddie, can you shut the door? Thanks. So when we calculate delta H, you have to kind of manipulate the equations and make it almost like a puzzle. So for this first one, I'm going to just kind of talk to you about how to do it, and then you'll get a bunch of sample problems. The first thing you should look at is always your overall equation. So we need to get these 2 equations or 3 or 4 equations, however many they give you, to look like this one exactly. And it's kind of like balancing. You know, when I balance, I just start. I always say start left to right and just go for it and start writing your numbers. And if you have to erase them, erase them. Because when you start trying to manipulate it in your head, it gets so confusing. And then you just end up sitting there like, I'm not sure what to do, and you waste so much time. Just start with it and then pray it works out. So as a side note, this 3/2 thing, I'll talk about at the end of lecture. But basically, it just means that this is for 1 mole, so I have to balance my reactants for 1 mole. I'm not going to balance it so that everything's equal on both sides. I'm balancing it so that this is 1 mole of this. So I'll explain that near the end of lecture. All right, so first thing is, if you're going to need specific coefficients, you multiply by a whole number to give you your coefficient. So multiply by whole number to get correct coefficient. Second thing is, if you need to reverse the reaction, you multiply by a -1. All right, so when I start, I'm immediately going to just start with the beginning reaction. So that says 4NO2. So I find NO2, and here it is in the second reaction, right? But there's only 2 of them, and it's on the wrong side. Do you understand? So I need this coefficient to say what? 4. So I need to multiply this whole thing by a 2. And whatever I do to delta to the reaction, I have to do to the delta H. I have to multiply this by 2 also. But that's on the wrong side, right? I need it to be on the reactant side, and right now it's on a product side. So what do? I multiply by a -1. So can we all agree that I can multiply this by a -2? Because that's like multiplying it by a -1. And that'll flip it for me. What about O2? That looks tricky. I have O2s on this side and this side, and then if I start working with that and manipulating it, it's probably going to look confusing So this is where I'm just going to hope that things work out for me when I'm done. I'm honestly saying I'm just going to hope it works out. And if it doesn't, then I will start using more brain power. I'm going to go to N2O5. I need that to say 2 of them. Right now it says 1, right? So I'm going to multiply this by 2. Whatever I do there, I multiply the delta H by 2. So I'm going to hope that this works out, and I'm going to write my whole reaction out the way that it appears right now. So what's 2 times 3 halves? 6 halves? 3. So 3O2 yields 2N2O5. And then this is flipped it. So this is 4NO2 yields 4NO plus 2O2. Does everybody see how I just did that? So now I'm going to cancel what? No.
Why did you do a negative 2 again?
Because NO2 is on the wrong side. So I had to flip it. So I multiplied it by a -1 to get it to flip. So I'm just writing what I did to my reactions out again. Okay? So I have 4NO on the left and 4NO on the right, so these cancel. I have 3O2 on the left and 2O2 on the right, so this cancels, and now this gives me a 1. And I have NO2, and then I have 2N2O5, which is exactly that equation. So do you see how it just kind of worked itself out? It doesn't always, but you kind of hope for that. So now I have to multiply this delta H value by 2. And obviously I have to flip this one, because if this forward reaction is exothermic, then the backwards of this should be endothermic. Do you agree? So I have to multiply this by the -2. So take your calculators out, and you sum these. That's what it said in the directions. You sum them. So you add up whatever the result is from those multiplication problems right there. So try that on your calculator, and then we'll check. All right, so your answer is -219.0 kilojoules. Make sense?
Of course.
It's just a puzzle. Let's try another.
That's all it is.
It's like a puzzle every time. All right, so let's analyze this one. So you're just going to start, right? If you start looking at all of these, it gets confusing. So you start left to right. Sometimes I'll look at the product and try to figure out where that's supposed to be, but you can decide start left to right. So right away I know that I need how many carbons? So I'm going to do the find carbon. Here it is. I need to multiply this all by 3. And then always make sure that you put that 3 over here so that you don't forget to do it later. And then I'm going to look at 4H2. And there's only one spot for H2, so that's kind of easy. If there's multiple spots for a molecule, I would just kind of leave it alone and hope that it works out. But there's only one spot for H2, and I need 4 of them, so I'm going to multiply this by 2. And then I'm going to multiply this by 2. And then C3H8, what do I need to do that? I need to multiply this by a -1. And then this by a -1. All right, so let's write them all out again and then see what happens. So I think you have an empty slide for this, right? So you should throw that all in. 4H2 plus 2O2 yields 4H2O. I'm going to reverse this one, so that's 3CO2 plus 4H2O yields C3H8 plus 5O2. 3 carbon plus 3O2 yields 3CO2. So now you start canceling. So we need 4 H2s. We don't need any O2, right? So I look for O2s. I have 2 plus 3 O2s on the left side. Do you see that? So that's 5 O2s, and then there's a 5 O2 on the right side. So those would just all cancel out. I have 4 waters on the right, and I have 4 waters on the left in the second reaction, so I cancel out those. I have 3 CO2s on the left, 3 CO2s on the right, so I cancel those out. And then all that's left is 3 carbons, 4 H2s, and C3H8. So again, calculate this sum of your delta H. Don't forget that these are the sums. Sometimes students accidentally multiply them because we multiply so often. But this is the sum of your enthalpies. So try that and we'll check. Okay, did we get negative 103.8? I heard one no. Why? Did you multiply your delta H's by 2, negative 1, and 3? Yeah? And then you add them? You know, it's really a good idea if you get a gift in December for any reason, you should ask for a graphing calculator because it will help you tremendously to go back and see where your mistakes are. Like right now, Ashley, can you do that? Yeah. So go figure out where you made that mistake. Some of them don't let you go back to look, but a lot of them do.
I got $5.
You got that for $5? That's great. All right. Here we go. I'm still recording. Next one. Calculate it using enthalpies of formation. So this is really simple, but it's like the one where you did bond enthalpies. So if you made a mistake with like your coefficient or adding or subtracting, you could certainly make an easy calc error at this point. So make sure you have enough space to do this on your papers, and then make sure you type it into your calculator correctly. So when you see something in standard state, this is going to have this little naught symbol here. And what this means is that it's a hypothetical value that indicates how much heat would be lost or gained during the formation of 1 mole of a compound from the most common form of its elements in their standard state. So we are now figuring out, unlike bond enthalpies we figured out if I have like a CH bond, how much energy is stored in that single bond, right? But this one, I'm trying to figure out, if I have C3H8, how much energy is stored in this molecule? When I put this whole molecule together, how much energy is released? Or if I blow it apart, how much energy is going to be absorbed to blow that whole molecule apart? So these are not bonds, but instead they're the formation of that molecule or that substance. Understand the difference? So to make 1 mole of that compound would be like 1 mole of C3H8 because the coefficient's 1. 1 mole of that substance. So the tricky part for this is that this naught symbol is just given to you, and you have to figure out what conditions that meets, because we're going to need to plug those conditions in the next lecture that I give you. We're going to do a lot more math, and this little symbol tells you 2 of the values that you're going to use. So it's 25 degrees C and 1 atmosphere for standard state, and one more thing is that it's 1 molar concentrations. We don't need that for this unit, but we will use standard state for other things this year. And I just want to make sure that you understand that it's 1 molar concentrations. So this will be hard for you to recognize because 25 degrees C is different than STP conditions. STP conditions are 0 degrees Celsius and 1 atmosphere. Do you see how this can get confusing? You have so much information to keep in your head that now you have to keep track of what's the correct temperature for standard state and what's the correct temperature for STP. So only this year, I figured out a way to forever remember this for myself because I would always get confused too. So I realized that if I stick the 0 degrees C in here, it spells stop. I don't know, that helps me because ST25P doesn't spell anything. Okay? So stop is the 0 degrees, STP is 0, standard formation is 25. We'll never use degrees Celsius, we'll always use Kelvin, so this will turn into 298 and that will turn into 273. So you just have to remember that this is 298 Kelvin, which is 25 degrees C. The F stands for formation of making that compound, okay? Yeah, 273 plus 25 is 298. So for methanol, this is where these halves come in. When I'm making methanol, if I want to figure out, is your hand up? No. Oh. If I want to find delta H of formation for just methanol, I want to know how much energy is released in forming this. So say since it's for 1 mole of that compound, I can't use 2 pieces of oxygen, 2 atoms of oxygen, not pieces, right? Because O2 in standard state at 25 degrees C in 1 atmosphere, oxygen exists as a diatomic molecule, doesn't it? So O2 is what I have to use at standard state. But I only need how many oxygens to make 1 mole of this? 1. So I have to half the amount of this. That's why you have a half. Because I only need half of that to make this. And I need 4 H's to make this. And I need carbon, which in elemental form at standard state can exist alone. So you have to kind of recall what things at standard state temperature, 25 degrees C, how do they exist? Like we know that the diatomic molecules exist as diatomic molecules, but what about like bromine and iodine? What state do they exist at? At 25 degrees C. Liquid and then solid, right? I2 solid, Br2 liquid. So to make 1 mole of this releases negative 201 kilojoules per mole, and it's always going to be for 1 mole of that substance. That's why you use the halves. So when you find delta H values, you're going to look them up in a table or they have to be given to you. You'll see tonight for your homework, some of them are given to you and you have to like figure out the other pieces, or it won't give them to you and you either are expected to know it because of this table, or you're going to look it up using that table that I just posted on Google Classroom, okay? You can Google it too. Like you can Google delta H of formation for and then just type in the compound. So anything that it's in its elemental form at standard state has delta H of formation of 0. In other words, you're not forming anything because this is how it exists in elemental form. So calcium, metal, you're not forming it. There's nothing to form. Agreed? It's like 1 atom of calcium. Nothing comes together. So the formation value is 0. Anything in elemental form at standard state, formation values are 0. So your diatomic molecules at standard state will be 0 because this is how they exist under standard conditions. As a side note, you're going to see this, I think, tonight for homework or somewhere. Carbon in standard state is just C solid, right? But carbon, you know, exists as what 2 things do you know it exists as? From your intermolecular forces unit. Carbon is a what? What type of intermolecular force does carbon always exist as? Thank you. A covalent network solid. And what 2 covalent network solids did I tell you are carbon-based? Graphite and diamond. But graphite exists at standard state. So C graphite, like you use it at standard state, don't you? It will exist at standard state. Like you can go find it in nature. At standard state, it's graphite. But diamond does not exist at standard state. You can't make diamond at standard state conditions, right? Where do you find diamonds? Underground, under a lot of pressure and temperature, right? High temperatures and pressures. So C diamond does have a value. It won't be 0. The reason why I'm telling you these things is because nobody tells you ever again that these things should be 0. So if you're trying to look them up in an appendix or you try to find them somewhere on an exam, they're not going to be there because you need to know that they're always 0 for something in elemental form. Is that clear?
Yeah.
Thank you. All right, so here's your equation. You get this on the exam. In your equation sheet, it tells you this equation. It says delta H of formation of products minus delta H of the reactants. Do not confuse this with bonds broken minus bonds formed. Because what's broken? Reactants. And what's formed? Your products. So if you do it the wrong way, you're going to flip your equation and you're going to get this wrong. So just make sure that you always do bonds broken minus bonds formed. Remember I told you that's alphabetical? B and then F. So this is products. I would put a big bracket around this. So the sum of your products minus the sum of your reactants. And then again, you're going to use the coefficient in the balanced chemical equation. And then you'll find the delta H of F values in an appendix or they'll be given to you. So it just comes down to how good you are with your calculator and setting this up. So let's try. This is given to you already, so let's just look at the values. So we do sum of 2 times iron product plus the sum of, which is 1 times aluminum oxide, minus 1 times iron oxide, and then 2 times aluminum. But when you go to plug in the values, iron is a 0. This value you'll look up. The aluminum is a 0, and then that value you would look up. And then you just plug it in, and you would solve. So the next slide, I have to give you these values. Well, I have to give you some of them. So I'm going to write them above this for you. Otherwise, you would just look them up. So delta H of SO2 is negative 296.8. Water is negative 241.8. And H2S is negative 20.2. So go ahead and solve. All right, so negative 1,036.8. All right, this slide is just showing you some interesting information, and then we'll talk about how you can use multiple reactions to get more heat. So this is showing you that in the beginning of time, we had metals in the earth, right? And humans need to figure out a way to get the metals out of the earth and then use them. The only metal that exists in the earth as the metal itself is gold. The rest of them exist as oxides. So if you go and mine for gold, like you've seen cartoons, they can pickaxe at it and they get gold, right? But you can't get any of these other ones. They're all going to exist as the oxide. So this should make sense to you that the delta H value for gold is positive because we have gold. So the formation of the oxide actually requires energy to be put into it. But if I want to get silver oxide to become just silver, the positive value, so if I'm reversing this, this is how it exists in nature, right? If I want to get silver by itself, I have to reverse this process. So this becomes what kind of value? Positive, which means I have to input heat. So the only way that humans could do this from early times is just use fire, right? You just heat it up, and you drive off the oxygen, you get rid of the oxide, and then you have the elemental form of whatever metal you're looking for. So the problem becomes that each of these is what? Getting what? Higher. And so that means that you need to make a hotter fire. At some point, you're limited by your materials, right? Like your little bonfire is just not going to cut it anymore, right? So you need to make some sort of furnace, and then your furnace still isn't even going to get hot enough. So eventually, down here, when we need to get iron out of iron ore, which is iron oxide, you can't get it. There's no furnace that's going to just, you can't just throw enough wood in there to get the furnace to be hot enough. So they had to figure out a way to get a hotter fire, essentially, to create just the iron. So in the next slide, I'm going to show you how you can use Hess's law to create the correct amount of heat. So this is what it is. It's asking you to find delta H for the reaction between carbon and iron oxide to produce iron. So I want carbon plus iron oxide to just give me iron. So I take my Hess's law equations with this delta H value and this delta H value. Both of them are going to require heat if I'm going to go the reverse way, right? So you just Hess's law this all out. You end up reversing this reaction, multiplying this by 3, and then you can see if I have iron oxide, which I take out of the ground, and then I put in some solid carbon, I can get iron by itself, and look, I only had to input positive 462 kilojoules of heat, which is, if you look back at the last slide, similar to what we could get just in our furnace. So we could get iron by just combining two substances and getting a different amount of heat. Last slide. Sometimes we get delta H values for a reaction that's more than 1 mole, and you have to recognize that. So if you see, and this is what you're going to end up seeing these all the time on your homework. It'll give you a reaction, and then it gives you the delta H value, and it asks you to do something with it. Especially in lecture 3, I'm going to give you tons of these like this. So when you see this, you need to recognize, okay, this is the decomposition of peroxide, hydrogen peroxide, going to oxygen and water, but it's for 2 moles of hydrogen peroxide that's being decomposed. So this delta H value is not per 1 mole. This delta H value is for the balanced chemical equation, which has 2 moles being decomposed. Do you see that? So if I'm trying to figure out how much heat is released when 3.56 grams of hydrogen peroxide decomposes? It's a ratio. This looks a little different than the way I do it, but it's still a ratio. I still would like you to use a ratio. So when I solve for this, I'm going to say, well, this is negative 186 kilojoules for 2 moles. So what is my Q value for my moles? So how do you find your moles for this problem? What are you going to use? Just molar mass, right? So I'm just going to convert this to moles using the molar mass per 1 mole. And then I'm going to solve for that and put that right there, and then the problem's done. So 3.56 divided by 34.02. This is 0.105 moles, and you'll get the exact same answer as you do there, negative 9.73 kilojoules. Because this is 1/10 the number of moles of a mole, isn't it? So look at that value, 186, and then I get 9. Is that not 1/10 of it? I don't think you guys still get it. Some of you are like, sure, whatever she just said. I'm trying to make you recognize if I multiply a reaction times 10, I should get 10 times as much heat. If I double it, I should get double. If I times it by 10, I should get it times 10 heat. So this is how much heat I get for 2 moles here. Then I should see how much I get if I, did I say for 1 mole? That's why I said 1/10. I was thinking this said 1 mole, but it says 2. Do you understand why I said 1/10?
Yeah.
Okay. Well, maybe that's why you guys were like, I don't get it. So maybe you were right for not understanding that time. But I'm trying to demonstrate that it should be half and then 1/10. Yes? Now do you see it? Okay. Like half of this is what? 90-ish, right? And then 1/10 of that is? Like 9-ish. That's what I'm trying to demonstrate, okay? Because this is 0.1, and this is 2. Okay. Should delete this from the video.